Hi everyone! Today we're going to be talking about graphing radical functions. Our objectives for today are that students will be able to graph and analyze square root and cube root functions. Let's get started. The first radical function that we're going to talk about is the square root parent function. So the square root parent function is f of x equals the square root of x. So this is a parent function that you need to know how to graph. So first thing we want to do in order to graph this parent function, the square root parent function, is make an xy table. So make your xy table. Then if we were to plug 0 in for x, our y would be 0. And we also know that in a square root parent function, in a square root function, it has to be positive because we can't have a negative square root. So we start with 0, we go to positive 1. If we were to plug 1 in for x, the square root of 1 is 1. The next number we want to plug in for x is our perfect squares. We want to plug in a perfect square so that our y is a whole number, not a decimal, because it'll be really hard to graph decimals. If we were to plug in 2 for x, we would get an ugly decimal for our y, because the square root of 2 is an ugly decimal. So the next x we want to plug in is 4, our next perfect square. The square root of 4 gives us 2, a nice even number that's easy to graph. And then our next perfect square would be 9. So 9 is another x that we want to plug into our square root parent function. Square root of 9 gives us 3. Now, using our xy table, we want to plot these points. So this gives us points for us to graph. So anytime we're talking about our square root parent function, this is what it's going to look like. It's going to start at 0, 0. Oops, let me get my pen back. So that's our first point. Then it's going to go up to 1, 1. Then it's going to go over 4, up 2. And then over 9, up 3. If we connect all these dots, this is what the square root parent function should always look like. And once again, it's not going to be negative because we can't take the square root of a negative number. All right, so in order to label this, our end point, we know it's starting at 0, 0, so that would be our end point, this point right here. The domain, we know if our domain is looking left to right, we know that it starts at 0 and it goes forever in the positive direction. So it goes from 0 to infinity. So our domain would be including 0 to infinity. That's why we use a bracket, because we're including 0. And then our range, as we're looking up and down, we're looking at our y. We know it starts at 0 and it goes up forever. So it's going to be from 0 to positive infinity as well. And that's going to be our range. And it's including 0. So this is our square root parent function. Now, when we're talking about the cube root parent function, our function should look like this. We've got f, oops, let me get my pen back, sorry guys, f of x equals the cube root of x. So this is our cube root parent function. Anytime we're talking about a cube root function, this is the parent function we want to use and the graph we want to use. Now, when we're dealing with cube roots, we can have negatives, right? We can take the cube root of a negative number. So when we're making our xy table, all right, what we want to do is start with our perfect cubes, both positive and negative. So we know negative 8 is a perfect cube. We know negative 1 is a perfect cube. Always include 0, 1, and positive 8. Plug these in. So if we plug negative 8 into our function, the cube root of negative 8 gives us negative 2. The cube root of negative 1 gives us negative 1. Cube root of 0 is 0. Cube root of 1 is 1. And the cube root of positive 8 is positive 2. Now, these become our points that we want to graph. I don't know why that's doing that. Let's see. Let's erase this so it doesn't get in the way. Oh, and it's not going to let us. All right. Well, we're just going to graph these points. All right. Ignore that extra little weird stuff happening over there. All right. So let's graph these points. -8. So we go to the left 8, down 2. All right. Let me see. There we go. Then -1, -1. 0, 0, +1, +1, and then to the right, 8, up 2. So the parent function of our cube root function should always look like this. All right, this is always going to be our cube root parent function. And when we're talking about the turning point is still 0, 0. It's this point right here. This is when it turns to positive, when it turns to negative, right? When it goes up and down. So our turning point would be 0, 0. Our domain, it goes from negative infinity to positive infinity. It goes the left forever and to the right forever. So our domain is going to be from negative infinity to positive infinity. And our range, our graph's going to go up forever and down forever because this is going to slowly increase up. This is going to slowly increase down. So our range for our cube root parent function is from negative infinity to positive infinity. All right, rather than making an XY table every time you want to graph a square root function or a cube root function, we can use transformations to help us graph them. So anytime we have a square root, cube root, fourth root function, all right, we can use this form right here to help us with our transformations. So when we're talking about the h, we're saying that the h is the horizontal shift. So the transformations for cube root and cube root and square root functions are very similar to the transformations we've done previously. All right, so our h is talking about our horizontal shift. If it's positive, it's going left. If it's negative, it's going right. The k is the vertical shift. So if it's positive, it means it's going up. If it's negative, it means it's going down. So we start with our parent function and shift it. The end point, our turning point, is going to be h, k. So just like that's our vertex, right? When we were talking about vertex form of a quadratic function, when we're talking about square roots and cube root functions, that vertex is our end point or our turning point. If the a is negative, the function is reflected across the x-axis. So the sign of our a tells us which direction it's going, if it's reflected across the x-axis or if it's just like our parent function. If the absolute value of a is greater than 1, then we know that this represents a vertical stretch. If the absolute value of a is between 0 and 1, so if it's a fraction, this represents a vertical compression. All right, so let's do a couple examples and see how these different cube root functions and square root functions compare to its parent function. All right, number 1, we're looking at this square root function here. We know it's a square root function because there's no index. This -7 is our h. So this tells us that our graph is going to go to the right 7. Oops, I just meant to circle it. So that -7 tells us it's going to go to the right 7. The +2 on the outside is our k, and that tells us it's going to go up 2. Number 2, we're looking at a cube root function. All right, so this 4 in front tells us that it's going to be a vertical stretch because 4 is greater than 1. So it's a vertical stretch by 4. And the -1 on the outside is our k, and that tells us it's going to go down 1. Number 3, we're looking at a cube root function. The negative sign on the outside tells us that our graph is going to be reflected across the x-axis. All right, and this positive 3 on the inside of our cube root function tells us that it's going to go to the left 3. Last but not least, number 4, we're looking at a square root function. So how does it compare to our square root parent function? We're going to take our square root parent function and we're going to vertically compress it by 1/2. So we have a vertical compression by 1/2. The negative 2 inside the square root tells us that it's going to go to the right 2. And the negative 6 on the outside is our k, and that tells us it's going to go down 6 as well. So that's a lot of transformations on our square root parent function. All right, if you've had any trouble or you don't understand these transformations, please raise your hand and call me over and I'll help you and explain it to you. Otherwise, let's move on and see how these transformations are graphed. All right, I got a little ahead of myself. Before we start graphing, what I want you to do is number 5. All right, number 5 is we want to write an equation that represents the function described. So we know that we're going to start with a square root function. So we're going to start with the function f of x equals the square root of x. Then we know that the parent function is shifted 7 units left. So that tells us that it's going to be inside the square root, and that means we're going to go positive 7, because if our h is positive, that means left. Then we know it also goes 1 unit down, so that's our k. It's going to be on the outside, and it's going to be -1. And we also know that it's reflected across the x-axis. So a reflection across the x-axis tells us that our a is negative, so we put a negative sign in the front. So our new equation that represents this function would be f of x equals negative square root of x plus 7 minus 1. And that's our function. So if you were to ever see a problem like this, take it one step at a time. Start with the parent function and then adjust it to what each transformation calls for. All right, I want you to try number 6 on your own. Pause your video, and when you come back, I'll have the answer written on the screen. See if you can write an equation that represents this function described. So pause your video now. All right, you should have gotten f of x equals the cube root of x plus 2 plus 3. All right, so we know we start with a cube root function, so we're going to start with f of x equals the cube root of x. Then we know it has a turning point located at -2, 3. So what this means is our h is -2 and our k is 3. All right, so we want to write an equation that represents this function. The important thing to remember is that when we're dealing with our transformation with the form, right, when we're dealing with our transformations of square and cube root functions, it's always x minus h. So if h is -2, it's x minus a -2. That's why it becomes x plus 2. Then k is positive 3 that goes on the outside. That tells us we're going to go up 3. So the important thing to remember here is that it's always x minus h, and that's why it becomes plus 2. All right, now let's move on and finally graph some of these radical functions. All right, number 7. We want to graph these radical functions and identify the key characteristics. So number 7, we know we're starting with the parent function, f of x equals the square root of x. This is a square root function, not a cube root function. So the first thing I want you to always do is graph the parent function on your graph. And you're going to need 2 different colors anytime you're graphing radical functions. One color is going to be for the parent function. The other is for your function that's been transformed, all right, that you've applied the transformations to. So graphing our parent function. This is something you need to memorize. We know parent function, we're going to start at 0, 0. We're going to go 1, 1. When we plug 4 in. We get square root of 4 gives us 2, so 4, 2. And then we get 9, 3. This is our parent function of our square root function. All right, so always graph your parent function in one color. Then we know that in our new function, this plus 5 tells us that we're going to go up 5. So what I want you to do is look at your graph and move every point that you drew in the parent function up 5 units. So start with 0, 0 and go up 5. Oops, need my pen. So 0, 0, up 5. There's our new point. At 1, 1, move it up 5. There's our new point. Then we've got 4, 2. Move it up 5 units. There's our new point. And then take your last point, move it up 5 units. And there's your new point. Connect the dots. And now you have your transformed function. You have f of x equals the square root of x plus 5. I will always accept, actually I want you to put both the parent function and the transformed function on the same graph. Just use 2 different colors. All right, so we know this blue one is our final answer. That's what it should look like. And this is much easier than making an XY table every time we want to graph a function. We just transform our parent function up 5 units. All right, now when we're talking about the domain of this function, as we know, it starts at 0 and goes to the right forever. So our domain is going to be including 0 to positive infinity. Our range, it starts at 5, because it's not including any of these points below. It starts at 5 and goes up forever. So our range is affected by this transformation. So our range is going to be including 5 to positive infinity. Our end point or our turning point is this point right here where it starts. So that's going to be 0, 5. All right, that's our end point. Then end behavior. As x is approaching positive infinity, f of x is going up. So it's also approaching positive infinity. And then with square root functions, it's a little different. We say as x is approaching, when it's going the other direction, it's approaching 0 because it stops at 0. When we're going to the left, it stops at 0. So we say as x is approaching 0, f of x is approaching, our y is at 5. So we would say as x is approaching 0, our f of x or our y is approaching 5. And that would be our other end behavior. Now we know our graph is only increasing. It's only going up. It's never going down. So our increasing interval is from 0 to infinity. And we don't have a decreasing interval. So we say our increasing interval is from 0 to infinity. Draw a line through decreasing interval because our graph is never going down. This would be all the key characteristics of f of x equals the square root of x plus 5. And we're done. All right, the reason I'm doing all of these graphs with you and not just the odds is because every single graph does a different transformation, and I want to be sure to do at least one of each of them with you. All right, so number 9, we're dealing with a vertical stretch here. This 3 tells us we're going to have a vertical stretch by 3. And the plus 1 on the inside tells us we're just going to go left 1. So before we deal with our transformations, all right, I got ahead of myself, always identify what your parent function is. Here we're still dealing with the parent function of the square root parent function, or just the square root of x. So start by drawing your parent function on your graph. All right, we've got 0, 0, 1, 1, 4, 2, and then 9, 3. There's our parent function. All right, and then we know that our transformations are going to tell us we need to have a vertical stretch by 3 and left 1. So what this means is we're going to take every point and move it to the left 1. All right, and a vertical stretch of 0 is still 0. So that stays at 0. We don't go up at all. All right, now our next point, we're going to move it to the left 1, but we know that it goes up 1 originally, So we're going to take that and multiply it by 3, right? If we did 0 by 3, that's why it stays at 0. 0 times 3 is still 0. But what we're going to do is we're going to move it to the left 1, and instead of just going up 1, we're going to go up 3. So left 1, up 3 instead of just 1. All right? So here we see that it goes up 3. Here it just goes up 1. All right? And then let me get rid of that. Now this one right here goes up 2. So we multiply that by 3. So we go to the left 1, right? And then we start at 0 and go up 6. So that's why it's stretched by 3. Instead of just going up 2, we're going up 6. But starting at 0, not starting at our parent function. So starting at 0, instead of going up 2, we're going up 6. But we still have to go to the left 1. And then our last point originally goes up 3. Multiply that by 3. So when we're starting at 0, instead of going up 3, we're going to go up 9. But we have to move it to the left 1 as well. And that's our new point. Connect your dots, your new dots, and that's your new function. So vertical stretches are a little unique, all right, but nothing you guys can't handle. Now, we've got to describe all of our key characteristics of this graph. So the domain. Domain, we're starting at -1 and going to the right forever. So our domain is including -1 to infinity. Our range doesn't change. We start at 0 and go up forever. So our range is including 0 to infinity. Our end point or our turning point is our new starting point right here. So it's going to be -1, -1, comma 0. That's our end point. Our end behavior, as x is going to the right, as it's going toward positive infinity, it's going up. So it's going toward positive infinity as well. And then remember, with square root functions, our other end behavior is just our end point. So as x is approaching -1, f of x is approaching 0. Increasing interval. Our graph is only going up. So when it's only going increasing, it's never going down. Never going down. So our increasing intervals we use our x point, our x coordinate, so it's starting at -1 to infinity. That's our increasing interval, including -1 to infinity. And it's never decreasing, so we don't have to write one. All right, if you had any questions about this one, because I know it was a little tricky, remember to raise your hand and I'll be right there to help you. Otherwise, let's move on. All right, number 12. First thing we want to do is identify our parent function. So our parent function is f of x equals the cube root of x. This is a cube root function. So next thing we want to do is graph our parent function. So when we're dealing with cube root function, we know it starts at 0, 0. We've got 1, 1, and then we've got 8, 2. All right, so we know we've got -1, -1, and -8, -2. All right, let me count those, make sure I did it right. All right, it's easy to be off by 1 here. There we go. Connect our dots, and there's our parent function. Then we want to look at our new function and see what transformations we're going to apply to our parent function. So we see that this -2 in front, so our a is -2. So the negative tells us we're going to reflect across the x-axis. And the 2 tells us we're going to have a vertical stretch by 2. All right, so this is probably one of the more complicated transformations. So let's take this one very carefully. All right, so we're going to take our graph, and we know that we're going to take each point and we're going to reflect it across the x-axis and stretch it by 2. So however many we're going up or down, we're going to multiply that by 2. So take your first point, 0, 0. If we reflect that across the x-axis, it's still 0, 0. And if we multiply 0 by 2, it's still 0. So our origin, our starting point, our turning point stays at 0, 0. Then take this point. first thing we want to do is reflect it across the x-axis. So we know it's going to be going down. And normally we go up 1. So instead of going up 1, we're going to go up 2 because 1 times 2 gives us 2. Right? So here we went up 1, multiply that by 2. So instead of going up 1, we're going to go down 2 because we're reflecting it across the x-axis as well. Then this one went up 2. So we multiply that by 2. So we know our y is going to be 4. But we have to reflect it across the x-axis. So instead of going up 2, we're going to go down 4. Now take your other points. So here we went down 1. 1 times 2. Instead of going down 1, we're going to go up 2. And then last but not least, over here we went down 2. So multiply that by 2. Instead of going down 2, you're going to go up 4. So your new point is up here. All right, then connect all your dots. So we know this one goes down this way and up this way. And there's your new graph. Now we want to be able to identify all the key characteristics of this graph. All right, so if we're looking at the domain, we know that the domain, it goes from left to right forever. So our domain is still negative infinity to positive infinity. And our range goes up and down forever. It's going to go up this way, and then it's going to go, and it's going to go down forever this way. So our range is still negative infinity to positive infinity. Our turning point is still at 0, 0. That did not change with our transformations. And then our end behavior. As x is approaching positive infinity, so as x is going to the right, f of x is now going down. So we say as x is approaching positive infinity, f of x is approaching negative infinity because it's going down as it's going to the right. As x is approaching negative infinity, so as it's going to the left, f of x is going up. So we say that as x is approaching negative infinity, or as it's going to the left, f of x is going up, or approaching positive infinity. Now, when we're dealing with cube root functions, it's always either increasing or all decreasing. In this case, we know our graph is all decreasing because it's always going down. Our skier is going down the hill the whole time. All right? We're never increasing. Skier's never going up the hill. It's always going down. So our increasing interval doesn't exist, and our decreasing interval is all of our points from negative infinity to positive infinity. All right? If you're understanding this, great. I know this one was a little trickier. Remember, if you have any questions, call me over. Otherwise, let's move on to number 13.